Okay, welcome everyone to my continuation of what are my favorite theorems. As usually, right? My biased point of view. So take everything with a grain of salt. Actually, today I don't even want to talk about a theorem, but rather about a very applicable and very surprisingly easy philosophy in mathematics and beyond, as we will see. So, so-called Monte Carlo experiments. And what will be so surprising about it is that it's a very, very simple idea. As soon as you have seen it, you probably will immediately see that this is very applicable throughout mathematics and beyond. But what it really is the surprising part about it is that it's pretty young for mathematics standards of mathematics, something like 80 years by now. But well, it really looks like something Newton could have known, but it's pretty new in that sense and very applicable. So I'm going to show you mostly applications from mathematics because that's what I'm familiar with. But I will add some links in the description to more uh, applied applications of those Monte Carlo methods. But yeah, let's just jump right into it because it's really easy and simple and quite beautiful in my opinion. So probably the oldest version, well, whatever, the oldest Monte Carlo method actually goes back to Buffon. So there's a very famous problem he asked. It's called Buffon's needle problem. It must have been the 18th century. He wasn't up for Monte Carlo methods, but anyway, so let me explain the problem. So you have those lines, and they're equally spaced, and you have a certain number of them. So here you have a certain number of lines, and you're allowed to throw needles onto those lines. This is something like here's a needle, here's another needle, here's another needle, whatever, here's another needle. You throw them basically randomly on your floor made of lines. Well, floor made of wood, and those. So that's what he wrote. Suppose we have a floor made of parallel strips of wood. These are my lines, and they are all of the same width. Because they are all of the same width, I usually assume that they're just one unit apart, right? Whatever the unit is, they're the same width anyway. And you drop a needle, so my green sticks here, you drop it on this floor, and the needle has a certain length, so L, that's what I call L. And he was asking what is the probability that the needle actually now crosses uh, one of those lines between the parts of wood, right? So my lines here. Um, and the needles that do in this picture here are in orange, and the needles that do not cross are in green. And he was asking for the probability of this to happen, depending on this distance between the lines, which I just normalized to 1, and the length of the needles that you drop. And in this experiment, well, you just count it. I will show you a more a video type thing in a second. But in this experiment, um, it turns out that that 38% of the needles actually hit the lines. And the fun thing is, and that was the solution to his problem, actually the probability is 2L over pi, where L was the length and, well, pi is pi, right? So it actually gives you a method to compute pi. That was certainly not what Buffon was up for. I'm not quite sure what he was up for, but I would doubt so. He was more interested in this exact solution. The probability is 2L over pi. But if you now drop enough needles and you just estimate you just get those probability, you can solve for pi, right? So pi is 2L over the probability. And here, probability is, of course, just hits over n. And you can get an estimate for pi by just throwing enough needles. So just make n very big. So 2 is a constant, of course. L is the length of the needles, so that's constant. And n is the number of needles you throw, and you just count the number of hits, and you get an approximation of pi. In this case, roughly 3. So pi in this example is 3, okay? Roughly 3. So let me show you, well, how this works and what now the Monte Carlo method is in with respect to Buffon's needle. So here is the same problem again, right? So you have a certain number of lines, and you have a certain number of needles, and it's the same color code. So orange means needle hits the line, and green means needle misses the line. And this is exactly the picture you've seen before. And what I can vary now is, well, I could vary the length of the needles. As you can see, more needles will hit, less needles will hit. But let's just keep this roughly at the same point. What the Monte Carlo method now would be to increase the number of needles. So just throw a lot of needles, just a lot of needles. And then you get pretty good approximations of pi. Here's 3.1. This is a pretty good approximation. If you don't throw many needles, then you get a really crappy approximation. If you throw a lot of needles, then you get a pretty good approximation, right? Few needles, bad approximation. A lot of needles, a relatively good approximation. So 3.1. And kind of the Monte Carlo method is just do this often enough. Just take a random sample, and I can vary my random sample here with this lower bar, just whatever. So these are different random samples. So let's take this one, for example, and I can vary the number of um, thrown needles in this random sample. And as you can see, the approximate value gets kind of close to pi, right? So it's a 3.2 in this case, which is pretty good, actually, if you want to approximate pi by this slightly silly experiment, like throw needles. You can do this, by the way, and some people have done it. I will add a link in the description. In real life, right? You just have to build it and you really throw needles and you count. That's the only thing you do. The point for Monte Carlo is, and that's kind of the idea, you have some counting, some probability problem that you solve to get a numerical estimate to something that a priori has nothing to do with probability, like pi. And that's really the main idea that Monte Carlo wants to Monte Carlo uses. The Monte Carlo methods are kind of use some probability, some part of statistics or probability theory to get estimates for, let's say, hard numerical values like pi or whatever. You will see more examples in a second. Okay, so this is Buffon's needle problem, and you can get an estimate for pi by just throwing needles on the floor, basically. So let me give you another approximation of pi, another very classical one. So we have a circle here, as you can see, and the circle lives in a rectangle. So my rectangle is the outside thing. This was a really bad rectangle. So my rectangle is this outside thing here. And it's pretty easy to see. Well, the circle has some radius, whatever it is. Maybe I should use a different color. The circle has some radius, whatever it is, r. And so the area of the circle is r squared times pi, right? It's the area of the circle. And the area of the square, because it's a square, is, and it has length 2 times r, of course, because if the radius is r, then the length of the square, the side length of the square is 2 times r. So it has radius 4 times r squared, right? So you can get rid of r, doesn't matter. And the probability of a point that you just now, the shotgun method, you just shoot randomly, completely randomly on this square, the probability that the point lands in the circle is, of course, just the area of the circle over the area of the square, which, well, circle over square is, of course, pi over 4. And you do the same trick again. So p is pi over 4. P is pi over 4. So you solve p. Pi is pi over 4. No, it actually was correct. P is pi over 4. And you solve for pi, right? So put 4 here. So it's 4 times p equals pi. And how do you get p? It's a counting problem. So in this case, I have thrown something like, or of course, a computer. I haven't done it. You could do that in real life. If you, let's say you take a dart and you throw it on a rectangle where I've drawn a circle on it. But anyway, So I have kind of, a computer has thrown 6,377 randomly generated points on the square, and the ones that land outside are this 1,675, and so you get the probability p, and you can solve for pi, and you get a reasonable approximation of pi. So here pi is roughly 3.17 for the sample. And again, that's a Monte Carlo. That's a Monte Carlo idea. Just do something randomly, and if you just do that often enough, you can get a reasonable approximation onto kind of hard numerical data, like pi. What could be a harder numerical datum than pi, right? It's very similar. It's the same idea, just in a kind of different disguise. And yeah, so kind of the main applications of Monte Carlo methods in mathematics is to calculate areas. The problem with areas usually is like areas underneath a function, so calculating integrals, that yeah, so most integrals life throws at you are just not solvable explicitly anymore. I mean, so really solvable in the sense that you write down some function that in your variables would spit out the result. Most integrals are not solvable in that sense. So you need to find some good numerical approximations. And you could use Monte Carlo estimates. So let me explain how you can do that. So here I have my curve, my function, and it's a reasonable function, whatever it is, doesn't matter so much. And the approximation of its um, so it basically the integral is one, because it basically is kind of a bell curve or a Gauss curve, a Gaussian. Right? So if I would take the integral to infinity, there should be one, whatever. But what I'm going to use is this mean value theorem. So the integral from a to b of f of x is b minus a times f of c for a certain c. Okay, that's the mean value theorem, and so certain c. That's the mean value theorem. It follows because everything is kind of continuous, right? It's kind of this mean value theorem. Okay, so b and a are known. In this case, I think they're roughly pi. Again, so you have minus pi and pi roughly here. And I need to find the c. And how do I do that, right? How can I find c? I mean, I know that it exists, but how can I find it? Well, the idea is again to use a Monte Carlo method. So basically you throw random points, you choose random points, and at those points, so let's say this one, at those points you evaluate f of x. You get some result, whatever. Here's another one, f of x, and there are quite a lot, of course, because you have to do this very often. Here's another one, f of x. You do this very often. You get a lot of those numbers, and you just average over them, and that's your c. Right? Just average random sample of f of c's, right? That's the whole point. Just, okay, you know that some c exists. It's somewhere, you don't know where, what it is, just average over, just choose enough f of c's randomly, takes the average, that's your f of c. And it works pretty well. So here, the f of c is this line, actually. And this is just then saying, so this is, of course, just the area of the square here. So the area of the function is approximated by the area of the square. That's the mean value theorem. And the point is, Monte Carlo tells you, just do f of c often enough, and just have a random sample of f of c's, and that's what you get. And then you get the result approximately. The whole catch usually is that you really need to do this randomly. So you need to have some reasonably good generator for random numbers if you want to run this on a computer. They're actually pretty good. Obviously, a computer can't really generate random numbers because it uses an algorithm, but they still works still pretty well. So anyway, that's exactly the Monte Carlo philosophy. Just something random, some random sampling, throwing random needles randomly on the floor, or the shotgun method, right? Just or the dart method, whatever you want to call it. just throw darts at a square and count how many darts hits the circle, or like in this example, just choose randomly some points and average over those points. And this philosophy is just so ridiculously useful. And as I said, it's only about 80 years old, so it actually came from particle physics, I think. Link is in the description to the history. But Wikipedia lists that says this huge list of so link is of course also in the description. Huge list of applications from physical science at the top to law. Okay. And in mathematics, the integration is the one I showed you, but there are some others, and I will show you another one in a second. And it's just so ridiculously efficient, and well, it's maybe not super efficient, so I will discuss it in a second, but ridiculously widely applicable, right? So that's why this is so good. So whenever you have a problem and you don't really know how to solve that exactly, try a Monte Carlo method. Just randomly solve it and average. Basically, that's what you do. For when it comes to convergence, so here's an example. So you have three methods. You have a red method, you have a black method, and you have a blue method. I showed you um, the black method. So the black method was this one. Okay, this is for solving integrals. In this case, it's I want to calculate the area of an ellipse, and I can do it in two ways. I can do it using this method. I can solve a certain integral. That's the um, that's the red method, and there's a kind of the red method doesn't converge very fast, so this is kind of bad from the viewpoint of convergence. And there's a better method which I haven't showed you, and that's a blue one that converges very quickly. But anyway, so here's the real value. That's what you want to get, and it's, at the beginning you have some fluctuations, like look whatever, but it then converges relatively quickly, and it's actually pretty good in the end. Right? So just it's kind of the law of big numbers. Just do it often enough, and you get the correct result. And the only thing I want to stress again here is the idea is so ridiculously simple, actually. Just do it often enough and you get the correct result. And just the application to numerical approximations came up pretty recent, which makes it kind of surprising, and it's not as well known as it deserves to be. Maybe that's the reason why I wanted to do this video anyway. So, well, the real reason is I just like it. But well, I don't know. Whatever. I should stop waffling. Let me show you an application in discrete mathematics, actually. So Monte Carlo has a lot of applications. So let me show you an application in discrete mathematics. The birthday paradox. The birthday paradox is, well, you might have heard of it. It's pretty well known in some sense. So basically, you have a certain number of people. So here I have 23 people, and they are presented by dots. And each person has a birthday, and I just oversimplify here by saying that every month has the same number of, well, has the same number of days. It doesn't, by the way, matter so much for the result anyway. But so I just have a random sample of people. That's my random sample, and they have, of course, associated birthdays. And the question is how likely it is to have a double matching of birthdays. That's the red one. Or a triple matching of birthdays, or a quadruple matching of birthdays, or whatever. You get the point. So quadruple matching is actually pretty unlikely. So the number below down here is the one you calculate. Right? You could solve this problem by just calculating what the result should be. So in some sense, this is again a really bad example of a Monte Carlo method, but it's very illustrating, so I use it anyway. Because kind of the philosophy is most problems that life throws at you are not solvable anymore. At least not in a strict sense. You need to use some numerical methods, and Monte Carlo is one of them. Anyway, so let's ignore that. But let's say you were unable to calculate those numbers here. So orange one is roughly 50%, and there's a blue one which is roughly 1%. This was a really bad one. It's roughly 1%. So how can you compute those numbers? Let's say it would be impossible to uh, to to compute them explicitly. Let me show you how this actually works. Okay, so here are we, same picture as before. I can vary the number of people. And as you can see, there are more people. And then, of course, if you have more people, it gets more likely uh, to hit the same birthday. So this is red, double matching. A triple matching would be blue. And it also gets more likely to have a quadruple matching. But anyway, so let's go back to 23, because this is kind of the famous 23 where this one gets over 50%. So let's have a look. 22 is below 50, 23 is above 50. But anyway, I'm not interested in getting those precise values. I'm interested in approximating those values, assuming that I don't know them. So what do I do? Well, just looking at this. So in this case, by the way, it's not increasing the number, because then I would vary these numbers below here as well, right? And I want to fix one of those numbers. Let's say the one for 23. No, in this case, it's making enough experiments. So the random seed is basically the seed for the generator that generates randomly generates those birthdays. And what you need to do is you need to vary those. Okay, you just vary those. Let's say you have 100 experiments and you count how often something happens. So you just go through all 100 experiments and have a look at this number down here in the double matching while I scroll through it. 1 0 1 1 0 1. Oh, there was a double one. 1 1 0 1 1 1 1 0 1 1 1 1 1 1 1. And you go through it and you would count the number of zeros versus non-zeros, and it will be roughly 50%. So let's have a look at the triple matching, because that works pretty well. So triple matching has a probability of roughly 1%, so 1 in a 100. So it should appear roughly 1 times in these 100 experiments. So let's have a look. 0 0 0 0 0 0, and indeed it does somewhere. Yeah, there you go. With a random seed 20 for the random generator. So this is a 20th sample you would do. It actually, no, not the 20th, the 19th that you would actually do. It appears once, and otherwise it doesn't appear. Very good. So for 19 it does appear, the triple matching, and for all others it doesn't. And you indeed get roughly 1%, right? So roughly 1% probability of a triple matching for 23 randomly chosen people, right? Again, the Monte Carlo method here is just do it often enough. So if I would do now 10,000 of those experiments, then I would get a really good approximation to those numbers below here. Right? But here the experiment is to kind of to take enough random samples and just compare them. And by the way, I don't get any quadruple matching if I do this here. And the probability of getting a quadruple matching, as you can see, is just a bit too tiny. If I would do more experiments, then I could also verify this number. Okay, but that's all I wanted to tell you today. So Monte Carlo is basically the idea to do something often enough, and you get an approximate value for some hard numerical datum like pi, or some probabilities related to birthday paradox, or values under integrals or whatever. And it's such a good idea, and it's such a simple and good idea that it's applicable throughout mathematics and the sciences, which is in the end really what I wanted to tell you. Like, there is this really good idea, but just throwing a dart often enough, and to get an approximate value for the real solution. And it's just ridiculously simple, and I hope you liked it. In any case, I also hope to see you next time.